Hey everyone, I'm Adam. I represent Alex Zero Project, and we are building our own blockchain with extensive privacy properties, and we decided to kill it with the title of this talk. Although if you survive the title, hopefully it's gonna get a bit simpler later on. So maybe hand raising, that's usually before talks. So how many of you knows what ZK-SNARKs are? I mean, in non-formal way, like what they are used for and roughly. Okay. Not so many people, so maybe let's do a brief introduction. So it's basically a cryptographic primitive that allows someone to prove knowledge of some data without revealing the data itself. So knowing some secret, I can produce a convincing proof that I know this secret, but I do not reveal the secret. So we're gonna see an example in a moment. And this is pretty general primitive. I'm gonna use this horrible abbreviation
NAZKP for
all primitive. And
usually this primitive is coming in several different flavors. So the one that is the most known is ZK-SNARK. There are also ZK-STARKs and bulletproofs. Like when we would like to be super formal, actually the first two ones are zero-knowledge arguments, not proofs, but this is irrelevant for actually any realistic implementation. So let's just focus on the name zero-knowledge proof and remember that there are several kinds. So what do they do? Before what do they do, I need to sketch some background. So when we are talking about decentralized systems, we can define several levels of anonymity or of privacy. So the first level, which usually comes as a default with most blockchain systems, is pseudonymity. So that's an ability to act under a certain pseudonym. So usually this is just the address of an account. This comes as a default in actually almost every blockchain we know. So usually the pseudonyms should be hard to link to real-life identities. Of course, most of us probably know what are the problems. For example, if I interact with anyone from my wallet, then anyone can actually track the transaction back to my wallet and peek into my wallet and see how many tokens I have. So this is pretty far from perfect privacy. I mean, it gives some privacy. It's quite far from what we want. The user experience actually it's also pretty far from perfect because most probably users would like to have several addresses so they don't always reveal their entire ownership status when they transact with someone. And how it looks on-chain? Well, on-chain it looks like this. So we see that there was some address sending some amount of tokens to some other address. The next significantly stronger level is anonymity. So that's ability of performing public actions, but without revealing information about identity. So here on chain, we would see that someone sends one ETH to someone. So this is significantly better because, for example, if I would send tokens to someone this way, then there is no way to track it back to my wallet and no way to peek into my wallet. So that's significantly better, but still not perfect. What is perfect or close to perfect is privacy, which is ability of performing non-public actions. So if we would have this, then the only thing we would see on chain is that something happens. So like some kind of cryptographic hash would just land on chain, and for outside actors, this would look basically as any other action possible. So there would be no way of inferring what actually happened. So how many tokens was transferred and which way? So the main premise of this presentation is that using zero-knowledge proofs, which is the most prevalent privacy technology today, we can have anonymous DeFi. So the DeFi which looks like this, but we need some stronger cryptography to have private DeFi. So to have DeFi which looks like this, we need some stronger cryptographic primitives than what we are using right now. So let's dive a bit deeper into how this zero-knowledge proofs actually work on-chain. So the main idea here is that, as I said before, this primitive allows anyone to prove knowledge of some specific data without revealing the data. So how it is usually used, for example, by ZCash. Originally, it was proposed in the zero cash paper and implemented by ZCash. The idea is that on the chain, what is stored is basically only hash of the entire state of the database. And then the person who knows the database, and for example, my personal database probably would be the state of my wallet, how many tokens of which kind I own. That's my private state of my database. On the blockchain sees only hash of the state. And when I want to update the state, for example, by sending some tokens to some other account, what I do, I send to the chain the updated hash, so the hash of the updated state, and the proof that the update was legal, in the sense that there is a sequence of legal transactions which are not minting tokens out of the thin air and doing other forbidden things. So I know transactions which can transform the first state into the last state. So the chain sees only hashes of the states. So the chain has no idea what actually happens. But the chain is convinced that what happened is correct in the sense that I'm not cheating here. So this is basically what we get from zero-knowledge proofs in systems like, I said before, ZCash. Also, Tornado Cash is using similar primitives. Manta in Polkadot ecosystem is also experimenting with similar ideas right now. So this is quite nice when it comes to normal value transfer. So the concept is often referred to as shielding accounts or shielding transactions. So here on the left, we have normal transaction, which is unshielded. So here, when Alice wants to send one ETH to Bob, what she sends to the chain is like the request, please move one ETH from Alice account to Bob account, and it's signed by Alice. And, well, chain sees everything, and chain just updates the state accordingly. So everything is public, everything is transparent. It's obvious that Alice is not lying because she's providing the signature. But, well, the problem is, as I said before, when Bob can peek into the Alice account because Alice is revealing the address of her account in this action. So what happens when we are shielding accounts is that, as on the slide before, Alice is sending only the request to update hash of her state with the appropriate proof. So the chain sees only this weird request from which is pretty hard to actually, I mean, it's impossible to infer what actually happens. I mean, the chain knows that Alice is doing something, but there's no way to guess what is she doing. And actually, it's even hard to say it's Alice, because here there is just some enigmatic proof. So the chain sees some update of some hash and some proof. No link to Alice, and definitely no link to amount of tokens that is being transferred here. So when it comes to value transfers, this is basically as good as it can get. Everything is super private here. So this kind of solves the privacy for more normal transfers. What's problematic here is when we look at how DeFi actually works right now. So this is a very schematic presentation of the entire DeFi space right now. And I think this scheme, while it's simple, is actually, I mean, it shows actually pretty well how we see DeFi right now. So this is a very simple decentralized exchange. How it works is that some user sends tokens to the contract. This thing here is a smart contract. Smart contract is doing some simple computation. So it's computing how many tokens it should pay out on the other side. And here, the contract is sending the tokens back to the user. So while this one is pretty simple, basically all DeFi protocols looks like this. I mean, it's like for lending protocols, we are sending some tokens, there is some computation done inside, and then some tokens are given back to us. We're adding liquidity, we are getting some LP tokens out, we are perhaps getting some governance tokens or some other crazy bonus tokens as well. But the basic scheme stays the same. We put something into the contract. Contract needs to know how many tokens we're putting inside, and only based on the amount of tokens, it can compute the outcome of the action. So we can make it a bit more private using the previous primitive. So we can shield this person here. But the question here is, can we shield smart contract? I mean, it would be really nice to have everything here super private, so we cannot see what's going on inside of a smart contract and what is being traded. And this is actually very hard and rather not possible using zero-knowledge proofs only. Why? Because when we are computing these zero-knowledge proofs, how this primitives works is that there needs to be a single entity, like a person, which knows all the in and outs of the actual thing that is being proven. So there would have to be some kind of a manager behind this contract which would hold secrets, and that's not how we want to have our contracts. We don't want to have a manager holding secrets behind each contract. We want contracts to reside on chain. So while if everything from this contract, including its internal state, is on chain, everyone can read that by kind of definition. Blockchains are transparent, which is a big quality, but also comes at a cost. The cost being here is that it's very hard to make smart contracts private in this strong way. So, like, using only zero knowledge, we can make smart interactions with smart contracts anonymous, like here. So we can send to smart contracts, transactions from shielded accounts, but it's very hard, or like borderline impossible, to make them private, because the internal state of smart contract needs to be public, so it needs to know what is the input, so it can actually carry on the computation. So can we actually do something with that? So we'd like to have like a better, bigger, stronger shield here, which would shield this thing, and this thing. So the entire thing would be private then. So here the contract would compute something using its private state and would output the private output. So can we do it? Well, of course, I wouldn't be giving this talk if it would be like totally impossible. Although this is pretty experimental when it comes to cryptographic primitives, which needs to be used here. So right now there are two approaches to this stronger kind of privacy. One is called TEE, Trusted Execution Environments, and the other is MPC, which is multi-party computation. And these approaches differ very much, basically, in every aspect, with this exception that they both, in a way, allow smart contracts to operate on a private state. So first, in trusted execution environment is hardware-based privacy. The whole idea is that there are very specific microprocessors which have enclaves in them. So these are parts of a processor which on the hardware level allow to perform private computation. So basically, they allow to perform computation in such a way that even owner of this microprocessor has no way of peeking inside, of checking what's being computed inside and what's being stored inside. There are several projects experimenting with it right now. Perhaps the biggest one are Secret Network, Fala Network, and Hyperledger Avalon. And the security model here is basically we need to trust the manufacturer. Right now, as far as I know, there is the SGX manufactured by Intel is the most popular TEE example. So we need to actually trust that it's produced well correctly. So there is really no way of peeking inside it. And the main drawback is the vendor lockup. So basically, this system right now doesn't really allow to use TE from different manufacturers. They mostly focus on a single manufacturer. So well, definitely it's some kind of a drawback when we are talking about security model. On the other hand, the big plus of using trusted execution environments is that the computations are pretty fast. I mean, they're perhaps not as fast as a normal microprocessor, but like this is the same order of magnitude. So we can actually carry on complex computation with, well, which are private as long as we believe this security model. When it comes to multi-party computation, it's entirely based on software, so no special chips are required. And the main idea is that there is a committee, and the committee shares secrets among themselves. In such a sense that, let's say, there is a committee of 10 nodes, so they share a secret in such a way that 7 of these nodes would need to gather to actually reveal the secret. And there are specific protocols to perform computations on the secrets. So what happens is that the nodes share inputs to the computation as a secret. Then they perform computation using a lot of communication between themselves. And as a result, they share secret, the output as the secret. And then they can either reveal it or do whatever it's predefined for this output to be done. The projects which are using it is first Aleph0, that's us. The second is Partitia, and the third is HashCloak. As I said, all of this is pretty experimental, so none of these projects have deployment on the mainnet of a solution based on MPC just yet, but hopefully it will be this year. Security model, it's totally different. We don't need to trust any manufacturer. We need to trust in the committee. So as I said before, if 7 of the 10 people in the committee would gather, they could reveal all the secrets. So what we need to trust is that they don't do that. It's pretty simple, actually. The main drawback is that to compute anything, they need to talk to each other. And they need to talk to each other quite a lot. To perform a single multiplication, they need to have a round of communication. So if we would like to perform complex computation here, that would take like its order of magnitudes slower than trusted execution environment. The main plus here, I guess, is the security model, but that's I'm going to discuss on the next slide. So the big question here, I guess, is what can we get actually from such a shield? So this is a new primitive, so it should be motivated by some actual use cases. So it depends actually how much we trust that these secrets which will not leak. So here is the line from low trust to high trust. So let's start with low trust. Low trust means that, well, we believe that secret will not be immediately available to everyone. So they can eventually leak, they can even instantly leak to some insiders, but they will not instantly leak to everyone. So like, this is not a very strong degree of trust. So using this, we can have some kind of a weak dark pool. So like a trading spot where we can trade almost anonymously, so we can trade without moving the entire market. Only perhaps several actors will be able to act based on the information of what we're doing. That is perhaps not all that interesting. The interesting stuff happens here. So here we believe that secrets will not be immediately available to anyone. So they can leak after some delay, but instantly, no one will know what actually happens. So using this, we can, for example, countering MEVs is a very strong statement, but the concept here is that if the trade is executed in a way that no one sees what is actually being traded, that it's impossible to profitably front-run such a trade. I mean, if we want to front-run a trade, we need to know quite exactly what and which direction is actually being traded. It comes with a lot of different problems when it comes to actual deployment of such theoretical DEX, but yeah, at least like it gives some hope when it comes to countering MEVs. Second price auctions or hidden bid auctions is a different use case of this. So these are the auctions where at the time of bidding, the bids are not revealed and only the winning bid is revealed by the end. So perhaps like there's some NFT use cases here or like basically any auction. Perhaps governance-related auctions as well are a use case of this thing. Later. Even higher degree of trust is that we trust the secrets will not leak without a major financial incentive. So here, if we like will not leak means like never or almost never. So here we can do private votings, private DAOs, and stuff like that. Next step is that we so strongly believe that the secrets will not leak that we would like actually bet $1 billion on that. So even with such financial incentive, it would be impossible to leak the secret. So if we would be at this place, then this is actually small paradigm shift, because if we are in this place, that means that we can store private keys inside of these secrets. We can store private keys to the accounts. If we do that, we can have decentralized systems acting on user behalf in entire DeFi. We can have way simpler bridges between different chains. And like decentralized liquidation prevention, this is actually possible also with normal smart contracts, as we've seen on one of the talks today. But basically here, we can have a system which is blockchain and operates with the accounts of users. With the highest trust, like probably there is even higher level where we trust that these secrets will be never revealed with any incentives. Then perhaps we can perform some computations on the medical data on chain and things like that, things that we actually really want to remain secret forever. Okay, so what are the main things to take away from this talk? First is that the zero-knowledge proofs can give us anonymous DeFi, but they cannot give us private DeFi right now. The second thing is that MPC and TE can give us more depending on how much we trust it. And the last one is that actually, apparently, we trust quite a lot MPC because there are projects right now which literally store billions of dollars of value behind the committees. The projects such as Warhol and Multichain, which are multi-chain bridges, which actually operate exactly in this way, that they store private keys shared among the committee, and yes, well, people store their value there, and yes, there have been some hacks, but right now still over $1 billion of value is stored there, and it's, I guess, secure. I mean, there is at least some degree of trust from some of the committee at MPC, which is at this level. Okay, so thank you for listening. If you have any questions, I'll be happy to answer.
How many committee members can you have in a system like this? Because it seems to me like the more you have, the more sure you can be that you can indeed trust it. So if, for example, in Ethereum, each node needs to do all of the computation that the whole blockchain does. So here it might make sense that each node is a committee member, and if it's staked, that means that if they would need to all work together, to leak the secrets, and they would lose their stake, which would you know, be against their interest.
So that very much depends on what you want to compute. When it comes to signing, for example, a single message every few seconds, which is a reasonable use case, because, for example, when you are deploying a bridge, you don't need to sign every transaction separately. You can sign like batches of transactions. So we have coded threshold ECDSA, and it's up to 50 or 60 nodes are able to share the same key and produce a signature every, so like, I don't remember the exact result, but I think it was like every 2 seconds or something like that. So when it comes to just signing one message for the bridging purposes, then I guess the answer is like up to 50 that should be possible. When it comes to performing computations separately for each user, the number would be significantly smaller, and I would rather say that's something around 10. But also, like, it's reasonable to have a separate committees for storing the private keys and for computations which are not so security intense. I mean, it's the incentive to leak the secret from the committee which just have an internal state of the exchange but doesn't actually have a key to the account is significantly smaller. So it makes sense to have separate committee to keep the private key, which is bigger, and to actually hold only smart contract secret, which is smaller and faster.
So could you have thousands or like a commit 10,000 members of the committee or 100,000?
I don't
That's
think.
not feasible.
I mean, it scales quadratically, so unfortunately, I think it's not really possible.
You.
Hey, thanks for the nice presentation. So I was wondering, I have a few questions, short ones. So you implemented your own blockchain network supporting the privacy, or you are built on top of Ethereum, let's say, on a software level?
We have our own chain, which is based on Substrate, and we have repositories which are implementing threshold signatures, but they are not related to our chain yet. We are still working on having a working prototype.
Is it EVM compatible? Can I use the Solidity code base? No?
We're working with WASM.
Okay. And the last question, is there some kind of like a paradigm shift or like the way we think of dApps within this new privacy-based model? Are there some new use cases, or could you like map every dApp existing on Ethereum to your privacy-based solution?
The mapping is not so trivial because there are problems, for example, related to arbitrage. I mean, arbitrageurs are like very wanted actors in the system. So if every state stays private, it's very hard for arbitrager to make arbitrage and recover balance inside of the pools, for example. So there are several non-trivial economical problems when it comes to like simple translation of the DeFi we have on Ethereum right now into the DeFi in this paradigm. So this, for example, decentralized exchange would have to leak some information which would be non-user identifying, but would help arbitrageurs to actually recover the required balance in the pool. So yeah, it's not as trivial as it could look like.
And from the developer perspective, for example, I'm a Solidity developer. Do I have to like accept new paradigms, or like do I have to learn some different mechanisms in order to onboard and like start building dApps?
So it's pretty early to answer this question, although what we are aiming at is the experience of using a library, let's say. So the library where you can define a variable which actually is private, and then there will be special ways to interact with this specific kind of a variable.
Thank you very much.
So I kind of imagine having to debug such a system is quite difficult, and maybe there have been like live problems or hacks. Are there any instances that caused, or any anecdotes?
So Fortunately, it's not all that bad when it comes to MPC, because it's not like this cryptographic primitive MPC is nothing new. Like we knew about MPC like 30 years ago, and the MPC from 20 years back is actually probably even good enough to be deployed when it comes to cryptographic theory. The reason why it's not deployed is perhaps that DeFi was not actually advanced enough, and besides DeFi, like it didn't find such a major use case to be deployed on the large scale. But when it comes to like theoretical understanding of cryptography behind it, I think we are like pretty, I mean, it's pretty well understood in academic world. There are libraries which, I mean, like the libraries which are deployment ready or close to being deployment ready have been, I think, like 8 years ago, Scale Mamba was created as the first like a big library implementing MPC. So it's also not as bad as it would seem.
Any other questions, maybe? Okay. Thank you very much for your presentation.